All right, let's get right into it. If you're a junior software engineer gearing up for a high-stakes technical interview, well, you already know the pressure is on. But here's the secret. The gap between a junior engineer and a highly paid senior developer isn't just about years of experience. It's entirely about how you think about systems. Senior engineers get those massive offers because they can reason through architecture, not just grind out code. So consider this explainer your urgent, fast-paced exam bootcamp. We're going to build your mental model so you can absolutely ace that interview. Okay, let's dive into our syllabus for conquering system design. We'll be moving quickly through 6 core concepts today: statelessness, caching, the CAP theorem, message queues, databases, and API design. But before we hit the technical details, we need to talk about why so many engineers literally freeze under pressure. You know the feeling, right? The junior mindset relies heavily on memorizing terms. You memorize what DNS is, sharding, CDNs, idempotency. You end up building this incredibly rigid glossary in your head, but the second the interviewer asks you to design a novel system, you just blank. The senior mindset, though, focuses entirely on the why. By building a functional mental model and really reasoning through architectural trade-offs, you stop panicking. You start designing with confidence.
Concept 1. Statelessness. This is all about scaling without the baggage.
Look, everyone knows horizontal scaling means throwing more servers at the problem, but adding more servers only works if your architecture actually allows it. Here is the definition you absolutely must internalize. Statelessness means the server remembers literally nothing about previous requests. A server has to treat every single incoming request like it's meeting that user for the very first time. Every request carries all the necessary context it needs to be processed, usually bundled up in something like a token that lives entirely on the client side.
So what does this actually look like if you get it wrong? Think about sticky sessions. If your server stores session data locally, say an in-progress shopping cart, that specific user has to be routed back to that exact same server every time. Your load balancer's hands are totally tied. And worse, if that server crashes, boof, the data is gone. Now compare that to a shared store. By offloading that state to something like Redis or a distributed cache, your servers suddenly become completely identical. You can spin them up or tear them down without losing a single byte of data, giving you brilliant fault tolerance.
Moving right along to concept 2, caching, which is really just trading freshness for speed.
Caching is everywhere. It's in your browser, your database, everywhere. But it always boils down to one fundamental trade-off. You're storing a copy of some data somewhere closer and faster, and in exchange, you're accepting that it might be slightly out of date. So, during an interview, instead of just blurting out a technology name like Redis, I want you to pause and ask your interviewer, where is the actual bottleneck here, and exactly how stale can we afford this data to be? I guarantee that instantly proves you understand the underlying architectural choice.
And once you've nailed down those requirements, you can apply one of 3 main cache layers. You've got CDNs for serving static assets geographically close to your users. Then you have application-level caches, like Redis, sitting right in front of your database for read-heavy, millisecond latency. And finally, database query caches that live inside the database engine itself. Master these 3 layers, mix in strategies like TTLs and cache-aside patterns, and you'll easily cover the vast majority of caching questions you'll ever face.
Let's tackle concept 3, the CAP theorem. Get ready, because we're about to shatter the myth of choice.
So, most people learn the CAP theorem as pick 2 out of the 3. Well, I'm here to tell you that for real-world networks, that is completely wrong. Actually, scratch that, it's dangerously wrong. Partition tolerance isn't optional in any real distributed system. In the real world, running over a physical network, partitions will inevitably happen. Nodes will lose connectivity, packets will drop. Therefore, partition tolerance is a mandatory constraint, not a choice you get to make.
Now, what's really interesting here is the actual choice you have to make. You're choosing between consistency and availability. Consistency means every read gets the most recent write, period. It is completely non-negotiable for things like financial transactions or access controls. Availability, on the other hand, means the system always responds, even if the data it gives you is a tiny bit stale, which is absolutely perfect for something like a social media content feed. In an interview, never just vaguely say, "I'll use eventual consistency." Be precise. Tell them exactly which operations need which guarantees. Because in massive applications, you're almost always mixing both.
This brings us to concept 4, message queues. Let's talk about building truly resilient systems. Think of queues as your absolute best defense mechanism against cascading failures. To see why, let's look at what we call a brittle synchronous chain. Imagine a user places an order.
That service calls inventory, which calls payment, which calls notification, all in real time before the user ever gets a success response. It's like a line of dominoes. If just one service, say notifications, is running slow or goes down, the entire order flow fails. Your system's end-to-end reliability is now severely limited by every single dependency in that chain. No way.
So how do we fix it? Message queues. Tools like Kafka or AWS SQS step in to break that nasty dependency. Instead of calling services directly, your order service simply publishes an order-placed event. Boom, done. The queue holds that event safely. Downstream services then pick it up and process it totally independently on their own schedule. If the notification service suddenly crashes, no big deal. The message just waits safely in the queue, and the initial order still goes through perfectly for the user.
Next up, Concept 5, databases. The core question here is always, what data guarantees do you actually need?
Look, forget the whole false narrative of old versus new or simple versus scalable when it comes to SQL and NoSQL. If you are leaning towards a SQL relational database, you need to deeply understand this acronym, ACID. Atomicity means a transaction is all or nothing, absolutely crucial so money doesn't mysteriously leave one account without arriving in another. Consistency means the database always moves between valid states. Isolation ensures you get clean concurrent writes when thousands of users hit the database at the exact same time. And durability, that means once a save is committed, it survives even if someone unplugs the server.
And this brilliantly illustrates the exact trade-off you need to articulate in your interview. With SQL, you get those strict ACID guarantees, making it undeniably perfect for financials or inventory management. But with NoSQL, you intentionally trade away some of those guarantees to drop strict schemas and relax consistency. And why would you do that? Because it's exactly what allows NoSQL to achieve that massive, effortless horizontal scaling for things like user activity feeds or massive product catalogs. Again, large production systems, they almost always rely on both.
Let's move to our sixth and final concept, API design, establishing the permanent contract.
You have to realize that an API is not just some code you write for fun. Once it's shipped, it is a binding contract. Changing it requires a highly coordinated migration because it affects everyone downstream. So when you're comparing architectures like REST and GraphQL, you need to show the interviewer you know exactly what they optimize for. REST is simple, it's highly cacheable, and incredibly easy to reason about, making it excellent for stable, well-documented public APIs. GraphQL, on the other hand, is incredibly flexible. It allows multiple diverse clients, like a heavy web app and a lightweight mobile app, hitting the exact same backend to request exactly the specific data they need and nothing more. But regardless of whether you pick REST or GraphQL, there are a few golden rules of API design that apply absolutely everywhere. 1. Be explicit about versioning from day one. Just do it. 2. Design your endpoints around resources, not your messy internal backend operations. And 3. Document your contracts thoroughly before a downstream team has to blindly reverse engineer them and guess what your API does.
Well, that brings us to your final exam challenge. To truly cement this new mental model, you need to apply it to real-world applications today. Ask yourself, how exactly does an app like Spotify utilize caching across its different layers to deliver seamless music anywhere in the world? And when does an app like Venmo absolutely demand strong consistency versus when can it safely relax? Reason through those questions using the 6 concepts we just covered, and I promise you, you'll be more than ready to step into that interview room and crush it. Thanks for learning with me in this explainer, and keep building.